Scientists of tomorrow's world will continue to be as extremely interested in time and quantity as they are today. The world we see when we look around us is constructed of three dimensions: length, height, and depth. Time is usually called the fourth dimension. Time is always moving. We can't stop the passage of time. Much could be said about how we measure the size of an object. Much could be said about time. But let's restrict our discussion to a particular time elapses. As an example, let's plot a graph showing the height of a growing bean plant as the weeks of the season go by. After we plot a series of points, we draw a line connecting these points, and here is our graph. Now we have a graph, a curve showing how size varies with time. Engineers, scientists, and investigators spend a good proportion of their working hours taking measurements and then plotting a graph showing how those measurements changed as time elapsed. Man is eternally curious about the origin of the universe, curious about the origin of life and life processes, curious about atomic structure, curious in 1,000 directions. Our great curiosity makes us try to interpret the graphs recorded for us by old Mother Nature. These natural graphs of size versus time range all the way from billions of miles and billions of years down to billionths of inches and billionths of seconds. We are unable to comprehend a billion years or one billionth of a second. Yet we can use these terms to help us understand today's and tomorrow's world. Let's take a look at how graphs are plotted, first as recorded by nature and then as recorded on instruments devised by man. For an interesting discussion of how nature plots a graph in geological terms, here is Dr. Allen.
Man has always been interested in the rhythms of time. The earliest records show that the early astronomers developed the movements of the moon and of the planets. Nature has recorded the rhythms of time throughout all of life. For instance, a piece of wood will show the seasonal rhythms in its tree ring. A specimen of almost any kind of shellfish will show the rhythmic nature of growth, which may be seasonal or of longer periods. Not only does life show the rhythms of time, but the very rocks themselves, going back into the farthest depths of the past, show the rhythms of time. Here is a specimen which shows alternate layers of coarse and fine-grained material laid down during periodic intervals. Here is another piece which shows the fine banding produced by these rhythms of time. Time, of course, is almost limitless. The astronomers tell us that the Earth and the universe is 10 billion years old. Geology indicates the depths, the inconceivable depths of this time. And part of my story tonight will be to try to bring you a conception of what geologic time is, so that you can better conceive of the minute periods of time developed in this laboratory. Radioactive dating, for instance, has shown that the rocks were already hardened on the crust and that geologic processes were going on as they are today at least 4 billion years ago. Other evidence seems to indicate that the Earth itself may be as much as twice that age, and that life originated at least 2 billion years ago. Can you conceive of 2 billion years? I recognize that I can't. This is 1,000 million sets of seasons. Perhaps if we take a more familiar instance, you're all familiar with a time-lapse camera. A camera which takes one picture a minute or one picture an hour, and then speeds it up so that when projected normally, such slow events as the flow of clouds across the sky or the opening of a bud in a flower can be seen in detail. Let us take then such a hypothetical time-lapse camera to depict this last 3/4 of a billion years, a period of which geologists do know a great deal. We will take one picture a year, only one picture a year, and we will project that at the normal rate of 16 pictures a second. This will give us about 1,440 years per minute, 90,000 years per hour, 2 million years per day, and our film will last for a whole year. So we will start then in January 1st, 3/4 of a billion years ago. We are all long past the 3/4 mark in the age of the Earth. The crust is already more than 5 years old. Life itself, although no positive evidence exists, must be at least 2 years old. And as the scene opens, many of the various kinds of backboneless creatures of the sea have already swarmed on their shores, and by March they first learned how to grow hard shells and calcareous deposits so that we can find their diversified remnants preserved in the rocks. By July 1st, the first fishes appear, and plants learn how to grow on land in swampy places, so that by September, the eastern part of our continent is mantled with dense tropical coal forests, and the age of reptiles is about to begin. By October, the dinosaurs are about to take over the land, although certain small, important, reptile-like mammals presage later events. Later on in the month, birds and flying reptiles appear. But late in November, the reptiles begin to die out, and December is hardly come when they disappear forever. Early December shows the rise of the archaic, the titanic and gigantic mammals, but it is not until about Christmas time that modern forms begin to dominate the scene. On the last day of the year, man himself first appears, to be plagued by the repeated advance and retreat of 4 great ice sheets during the afternoon and evening of that last day of the year. At 11:50 p.m., modern man paints the walls and ceilings of his caves at Altamira, and at 11:55, civilized man leaves his first record only 8,000 or 10,000 years ago. During the last minute of our year-long film, the seconds tick by. Columbus sails the Atlantic during the 41st second. Jamestown is founded on the 46th. The American Revolution is on the 53rd. And at the 55th second, less than 150 years ago, steam and coal and iron is harnessed to usher in the Industrial Revolution that has resulted in all the technical wonders that we have today.
From a time scale of years and millions of years, we move now to a time scale of minutes and seconds. Suppose I try to record by hand a graph of changes in size which occur in less than a second. My arm is able to make such a record, but not with any accuracy. Faced with human limitations, man had to invent mechanical devices to draw graphs. Here is an early recording instrument called a kymograph. Recordings are made by a pen which scratches a visible line through a layer of carbon black deposited on the cylinder by a smoky flame. You are watching a recording of a turtle heartbeat. Notice the direct mechanical connection between heart muscle and pen arm. A great deal of excellent work was done with kymographs. but as you can guess, recordings were somewhat difficult to prepare and preserve. After electromagnets came into use, instruments capable of writing graphs on a strip of paper were developed. These instruments, called oscillographs, can usually record time intervals as small as 1/100th of a second. Using an oscillograph, here's how you could record a telegraph message. By looking at the recorded trace, we can read the information transmitted from a distant point. This is an oscillograph recording of a dog's arterial blood pressure made with a modern electrically driven oscillograph. Here's another type of oscillograph. We're looking at a multi-channel electroencephalograph, a brainwave recorder. Tiny electric currents from the brain are electrically amplified and used to drive each of the recording pins. Study of these readings can reveal certain abnormal conditions within the nervous system. Many electrical signals are repeated over and over again, as you have just seen. By drawing an example on the board, we can define the word cycle. A cycle is one complete waveform from here around to here. If cycles are occurring at the rate of 1,000 per second, then the time duration of each cycle must be 1/1000th of a second. Investigators in the various fields of science wanted still faster recording instruments, and keep in mind that faster means writing a graph in less and less time. Improvements in the design of oscillographs were made. Essentially, the weight of the recording pin arm was reduced. Here's an oscillograph using a beam of light to record on photographic paper. The beam of light is reflected by a tiny mirror, which is turned by an electric current passing through a coil of wire suspended in a magnetic field. Because the weight of the pin arm has been eliminated, inertia has been reduced, and the mirror is able to follow rapidly changing electric currents. These photooscillographs are capable of recording waveforms up to 1,000 or 2,000 cycles per second. Recordings of time intervals of less than 1,000th of a second, a millisecond, were being made by 1925. In that decade, a cathode ray tube was put to use as a graph or a waveform recording device. Investigators wanted to make recordings of waveforms which lasted only a few microseconds, millionths of a second. Mirrors and pin arms are far too heavy to move in a few microseconds, so a new approach was developed, the idea of using an almost weightless beam of electrons to draw our graph. Here's how a cathode ray tube works. The tube is an evacuated glass container or envelope. Inside is a device which generates the electron beam called the gun, a fluorescent material which gives off light when struck by the electron beam is called the screen. Many cathode ray tubes have elements for moving the beam called deflection plates. The gun consists of 3 or more elements. Its heart is the oxide-coated cathode. When heated by the filament or heater, the cathode gives off electrons. Around the cathode is an element called the grid. This controls the electron flow. Electrons have a negative charge. A plate or anode will attract the electrons when connected to a positive voltage. All of the electrons do not strike the anode. Some of them continue on through a hole or aperture in the plate and become the beam current. It is the beam current that produces the light on the screen. All the rest is wasted. Extra elements in the gun focus the electrons into a sharp spot as they hit the screen. These elements are called focusing electrodes. CRTs used in an oscilloscope have special deflection elements or plates inside the tube. These plates provide what is called electrostatic deflection. A voltage on one set of plates will move the beam up and down. A voltage on the other plates will move it back and forth. Here we have a complete cathode ray tube, a gun assembly consisting of a heater, a cathode which gives off electrons, and a grid to control the flow, focusing electrodes, an anode with an aperture that lets the beam current pass on to the fluorescent screen, vertical deflecting plates, an interplate shield, and the horizontal deflection plates. Early cathode ray oscillographs were large, bulky instruments nearly 8 feet tall. Continuous evacuation by pumps was necessary because the cathode ray tube could not be permanently sealed against the entrance of air. During the early 1930s, production of sealed-off cathode ray tubes began. With these tubes, compact and portable cathode ray oscilloscopes were constructed. And time interval measurements as short as a few microseconds became possible. Oscilloscopes were steadily improved as the years rolled by. Today, an oscilloscope is probably the most important single instrument used by physicists, engineers, biologists, and a host of other scientific workers. A cathode ray oscilloscope can record waveforms from the very slow to the very fast. Photographic records can be made to preserve the shape of the waveform displayed. Mechanical motion can be translated into an electrical signal and observed on an oscilloscope. Mechanical engineers use strain gauges to determine how much a metal bar stretches. The gauges are cemented to the face of the bar. When a force is applied to the bar, an electric signal is generated. As we bend the bar, notice that the spot on the cathode ray tube moves up or down, depending upon the direction in which we move the bar. We're measuring the change in length of one face of the bar, and the measurement is in millionths of inches. If we now cause the bar to vibrate, our strain gauge and scope will draw a waveform of that vibration or oscillation. Here is a display of the sound you are hearing now. Notice that the cathode ray tube records every change in voice pitch and amplitude. This is a single audio tone of 1,000 cycles per second. Since the oscilloscope you are watching can easily display 10 million cycles per second, the scope has hardly begun to work. Here is a display of 100 million cycles per second, about the frequency of a television transmitter. The length of time between the beginning of one cycle and the end of that cycle is 1/100th of a microsecond. While you blinked your eyelids just now, this oscilloscope drew a graph for you more than 200 times. Here is yet another oscilloscope, an instrument capable of displaying changes of size taking place in less than a nanosecond. A nanosecond is 1/1000th of a millionth of a second, or 1/1 billionth of a second. 1 nanosecond is almost precisely the length of time required for a beam of light traveling at 186,000 miles per second to move 1 foot. The waveform displayed on the cathode ray tube shows us the length of time required for an electric signal to go down a short piece of coaxial cable and return. We are presently developing an oscilloscope capable of displaying picoseconds, a millionth of a second. If we lived in a world where a picosecond was equivalent to one of our normal years, a flash of lightning would last for 50 million years. In tomorrow's world, we can foresee continued investigation of problems now being studied. Questions exist for which we want answers. What is the nature of a nuclear reaction? What is gravity? Does gravity have speed? Can anything go faster than the speed of light? What is the nature and the shape of space? Is our universe expanding? Is there a beginning and an end to time? Is the speed of light constant? Other questions will arise as these are answered. We've taken you on a tour of times and quantities ranging from billions to billions. These times and quantities will continue to be of interest in tomorrow's world, and cathode ray oscilloscopes will continue to provide some of the answers. Our primary job at Tektronix is to provide the scientist with better and better tools with which he can obtain answers which will shape our lives in the world of tomorrow.